Welcome back. Last time we were working on this problem here where we were comparing the number of people in the county to the number of crimes committed in the county. And my scatter plot looks like this, and those look really close to a straight line with positive upward slope. So yes, this has positive linear correlation, or at least we are pretty confident it does. We're actually going to do a hypothesis test on him a little bit later just to verify that, but he sure certainly looks like it. All right, now we want to find out what the R value is, just how strong that positive linear correlation is. So we're going to put our calculator to work here, and let's see if we can get this to, there we go. I've put in list 1 and list 2 the X and Y data. Now, let's go to stats, calculate. Okay. Now there's one option, number 4, that's linreg ax plus b. That's the one mathematicians use, but statisticians prefer to use, in this case, it's option A, linreg a plus bx. They will eventually get you the same result. You just have to remember which one's the constant term and which one's the slope term. Okay. Now it's going to sit there and blink at me because it needs to know what lists. So I need to tell it that the X data is in list 1 and the Y data is in list 2. And it's going to come back and think here for a second and tell me that A is negative 72.86 and B is 25.82. Oh, but the calculator was supposed to tell me what R is. It didn't do that. So if your calculator didn't do that, what I need you to do is go down here to the 0 key. And notice how in little letters it says catalog. So we're going to do second and then the 0 key to bring up the catalog. We're going to scroll down to the D's. Okay. And we're going to try to find the command that says diagnostic on. Okay. And if I run that, it says done. So now if I go back to the stats, calculate, and do the linreg a plus bx again, and I tell it list 1 and list 2, it will from now on give me the A, the B, R squared, and the guy that I was after, the R value. So let's write that R value down of 0.971 to 3 decimal places. So we have A equals negative 72.87. B is equal to 25.82, R equals 0.971, and while we're at it, R squared is equal to 0.942, 943. Okay. All right. So, and here's that little note on how to get the R and R squared to show up. And once you've set that diagnostic on, it will always show up until you run the diagnostic off command. Now, with our R value being 0.971, what does that tell us about the shape of the data? Well, remember that when R is close to 1, we have a perfect linear, positive linear fit. Okay. And so since this is so close to 1, this would almost all the dots land on a line. Now, not quite, because we have a little bit of difference, but it looks like they're all really close to a line. So we have a very strong positive linear correlation. Now, there's no hard and fast rule, but R values between 0.7 and 1 are strong positive. Between 0.4 and 0.7, that's a moderate positive linear correlation. In here, close to 0, this is practically, it's weak or no correlation. Okay. Negative 0.4 to negative 0.7, that's a moderate negative linear correlation. And between -1 and -0.7 is a strong negative linear correlation. All right. So now that we found R squared also tells us some interesting stuff. So let's go ahead and find out what R squared does. R squared tells us the percentage of the Y variable that can be explained in terms of the model that is the relationship between the X and Y variable. So for example, here we had R squared was 0.943. So if we wanted to interpret this in real world terms, let me give you a fill in the blank and then you can use that. So it's R squared as a percent of the variation or change in Y variable, whatever Y variable stands for, is explained by change in whatever X variable is in our linear model. Okay, so here's our kind of fill in the blank thing. So what would it be for this particular problem? 94.3% of the variation in Y variable, which was number of crimes, is explained by change in X variable, which was number of people in the county, in our linear model. Okay, so do you see how we just kind of filled in the blanks there? So that's how we interpret R squared. Now we're ready for our hypothesis testing on correlation. Now there's 3 requirements for this to work. Okay. First one, we need to have random sample of bivariate data. Okay. The next thing is that our technically what you have to do here is check that the X data is normally distributed for fixed values of Y and Y values are normally distributed for fixed values of X. But for an introductory statistics class, what we're going to do is we're going to check to see if the scatter plot looks something like a line. Okay. Now, somewhat is a little bit subjective. Okay. And the third one that our textbook recommends is outliers are removed if they are known to be errors. For example, if somehow our data said that there were negative 6.3 people in a county, negative 6.3 thousand people in a county, we know that would be an error. So if we have data that is known to be error, we pull it out. Otherwise, we leave it in. Now, R is a blank because he's computed from a sample. So he is actually a statistic because he's a measure of the sample. We didn't have all of the counties in Utah that we measured. Now, what is he measuring? He is measuring or standing in for the population parameter. And this symbol, I apologize, but he looks kind of like a P, but he's a rho, the Greek letter rho. And so we're going to use rho in our hypotheses. Our null hypothesis is that rho, the correlation, is equal to 0. And then our alternate hypothesis is that the rho is greater than, less than, or we're going to focus on not equal to determine whether we have correlation or not. So more often than not, we're going to use not equals to. But you can do one-tailed things. You can check for positive linear correlation or negative linear correlation, but more often we will just test for linear correlation, positive or negative. That's the not equals to. Okay, let me stop there so we can keep our videos around 10 minutes, and we'll pick up in the next one.